Hi, this is Shuley Physics, episode on rotational statics in equilibrium. This is a continuation of Newton's second law. That's all it is, but we're going to be pulling in Newton's second law for rotation as well as translation. Of course, Newton's second law is F equals ma. And you might recall applying this in X and Y directions. If you've been following Shuley Physics, you've probably seen this problem-solving text before. When you approach a scenario involving forces where there's an acceleration or there's equilibrium, you first start by drawing a force diagram, label those forces, provide values for knowns, identify target variables. If there's something like on a slope, you might identify the most appropriate X and Y axes as the second step. Usually orient that along the direction of the acceleration. After that, you resolve all those angled forces into their X and Y components, and that sets you up to use Newton's second law in the X and the Y direction. Oftentimes you'd end up with a system of equations to then solve for the unknown. And that's kind of what we're doing here, except we have one more tool at our disposal. And we're going to have to make our force diagrams a little bit more detail-oriented. That's the couple of the little differences that we're going to see. Instead of just having an F equals ma, we now have scenarios where there might be objects involved that are rotating in the system. So recall also that some of the torques acting on a body, or the net torque, equals I alpha. So applying both of these, you might often get an expression with the X direction, with all X direction forces involved, the Y direction, and now consider, what about the torque? Setting up torque equals I alpha. Now, oftentimes, when we do get into dynamic scenarios where there's an acceleration instead of equilibrium scenarios, the alpha and acceleration often, correspond. So how do you connect two expressions, one having like a mass and acceleration, one having I alpha? Do also recall that like an edge or tangential acceleration equals R alpha, and that's often the connector. By plugging in alpha equals A over R, that would connect this expression over here to these over here with that acceleration rate. So that's kind of the general background of what you're going to see here in the examples I cover in this lesson. First example I want to give you is a pulley. Now this pulley has some mass to it, and it is a disc pulley. Oftentimes in this kind of scenario, a moment of inertia might be given to you, some kind of I value in the beginning, and it could be some arbitrary value. We could just say 4 kilograms meters per second squared. It could relate to the radius of the disk, the mass of it. Of course, I for a disk is 1/2 mr squared. So you put those together, you might get a value something like 4 kilograms meters per second. 4 kilograms meters squared. Knew something was wrong with that. Now this particular disk, I'm going to run some line over it a few times, and the line that comes down along this edge is going to be carrying or holding up a mass m, and I'm going to give that value mass 5 kilograms. Do that. Now let's say going around the other side, going around this edge, it's going to be another winding, and right off on this side, the opposite side here, we're going to hang another mass, and I'll just give this a mass 1 and call this one mass 2. But this one's unknown, and what I want to try to do is balance the system to figure out what mass 2 is equal to. So in this scenario, I'm going to define that mass 2 is our unknown. Now a couple other things we need to know are the radii of these disks. So if we looked at these kind of head on, that's what we're going to do in a moment. Probably more easily see this, but I'm going to label this as R2 out here, and we'll label this radius out to this edge as R1. So looking at this directly in, we'll have a disk, and an outer disk and an inner disk, and they both share the same axis. They're attached to one another, and we're going to be hanging masses from this direction. We're going to have mass 2 hanging off this side, and mass 1 hanging off this side. think that's a little easier to see. All right, and our inner radius R1 and our outer radius, outer radius R1 and inner radius R2. That's a bit small for our viewing audience, so I'm going to go ahead and label those a bit bigger, R2 and R1. There we go. Of course, it should give some values to these. We'll give an R1 equal to, this is the larger one, so I'll call that a ½ meter. And an R2, the inner side, is half of that, a quarter of a meter. All right, so what is this mass 2 going to be? What's the value going to be? That's our target. In this scenario, there's nothing translating at all. There's nothing going side to side, up or down. There's only a rotation. And whenever there's an equilibrium, what we're trying to do is find a balance. So that's our scenario here. What is mass 2 so that the system is in equilibrium? System is in equilib. There we go. So that's our target. We're going to apply Newton's second law for rotation. Sum of all the torques equal I alpha. There they are. And we've got a couple of torques here. There's a weight from mass 2 pulling this way and a weight from mass 1 pulling this way. What I'm going to do is draw a force diagram this time and identify the torques. There's going to be F2, we'll call it FG2, the weight of mass 2. Now we're going to have the weight of mass 1 over here, FG1. They look almost identical. This one's more of a picture, and this is the force diagram. Notice on this diagram I'm given some positions to these forces. I'm not saying this is just two downward forces. Okay, if this were a translational force diagram, we would have FG1 and FG2 both going down with their position where these forces are originating would be arbitrary. All right, this would just indicate that, whoa, this thing's going to fall down. But guess what? It's being held in place by an axle that's not free to fall. So if this were the diagram, there would have to be some kind of upward force from that pin, whatever's holding it in the middle. And that would keep it from translating, keep it in translational equilibrium. What we're trying to go for here, though, is rotational equilibrium as well. So we want the counterclockwise force from FG1 to equal the clockwise force from FG2. What will this look like? We're going to have FG1 going in the counterclockwise direction, and I'm going to call that positive. So here we don't have left to right or up and down being positive. We have clockwise or counterclockwise. We're choosing to be positive. Causes a rotation. FG2 hangs off the other side. It's on the other side of that point. So I'm going to have a FG2. Oh, wait. Hey, don't forget to put your torque arm in. Okay, that's what I almost did. We get so used to just doing F1 plus or minus F2 being the sum of the forces, but these are sum of torques. So this, of course, is going to be not just FG1, but FG1 R1, and I'm using a capital here. So now we've got a torque. And do I have to worry about some kind of like sine of an angle? No, because if we look at where that string is being pulled here and run the radius out to that point where the force is applied, the R and the F are perpendicular to one another. So sine of 90 degrees is 1. Where I'm coming from there, remember torque equals R cross F, which is RF sine theta. So sine of 90 degrees is 1. We're just going to have R times F as the torque. I'm going to clean that up just a little bit, make it a little clearer. Okay, so we got FG1 R1 is the torque from this first mass, minus FG2 R2. Remember, I'm subtracting it here because this is an opposite torque. If you want to think of it this way, if I'm calling this direction the positive direction for R1, then this direction over here to where the weight number 2 is being applied, you might call it a negative R, or the force, the radius is in the opposite vector direction. Okay, so that's also the source of our negative. It's coming from that sine theta in the end. Okay, so that's the sum of all our torques. I like to say clockwise one way and counterclockwise the other. That's where I'm getting my positive or negative values. And that equals I alpha, or I is 4 kilograms meters squared. But what's the alpha going to be? It doesn't tell us. Or does it? Actually does. We want the system to be in equilibrium. So not only is acceleration in equilibrium, but also angular acceleration, alpha. So this value here is going to be 0 for rotational equilibrium, for that state of rotational equilibrium. Let's shorten that equilibrium word again. There we go. So this is just a 0. We're trying to balance out all the torques. All right, let's replace. Oh, hold on. Let's stop a second. Let's remember that, take a moment to remember that problem-solving format here. We drew a force diagram. We labeled the force vectors with all known forces, unknown forces, and angles. All angles here were everything was straight down. Angles with the R I indicated there in the diagram is just 90 degrees. So all the important stuff is taken care of there. Now this is a torque diagram, so we'd also need to, should indicate the radii, and I have indicated that otherwise over here. So I do have the forces and their positions acting on this object indicated. So we're moving on. Is there any appropriate orientation for an X and Y direction? No, we've just got a rotational system, so there are no X's and Y's to worry about, and there's no other angles to resolve. So on to step 4, applying Newton's second law. We don't have an X and Y direction, but we have a Newton's second law for torque, and that's what we're doing here, applying Newton's second law. And along with that, we do want to substitute, number 4, substitute expressions for forces where appropriate. So at this point, let's pull in our mg for these F's. We've got mass 1 times acceleration due to gravity times R1 minus mass 2 times acceleration due to gravity, that's weight 2, times radius 2 equals 0. Start plugging in what we've got. We've got a mass of 5. I'll go ahead and use I'll leave G right here because I know a secret, and you probably might be guessing at that too. R1 is 0.5, and mass 2 is our unknown. And there's G, given an R, a radius 2 of 0.25 meters. So I'm using our given information at the beginning. And here's my secret. If we divide all these terms by G, those G's cancel. It turns out regardless of what planet we're on, we're going to get an answer here. 5 times a half is 2.5 minus m2 times 0.25 equals 0. We see that 2.5. If we add m2 times 0.25 to both sides and divide by 0.25, we are going to get a mass 2 of 10 kilograms. There it is. And hopefully that makes perfect sense now in the end that we're looking at it. Mass 2 is exactly twice the mass of mass 1 in order to balance the system, because, let's look back up the diagram, R1 is exactly twice R2. So the smaller, the inside mass has to be double the outside mass in order to balance out the system. That's just an example, hopefully straightforward, of how a pulley is moving here. Now if we extend this just a little bit further, if we were going into a non-equilibrium spot, let's say what if the cord on M2 were broken, then we would have a torque causing an angular acceleration to occur. And it would start spinning, we'd have a non-zero acceleration. Let's go into another one. All right, what is this? Well, here I'm going to do a little describing here. I've got a board, and I'm going to give a description to this board. This board is 5 meters long, incremented by 1 meter. That's what this white line is down here. And I'm going to give it a mass of, the board, kind of heavy board, I'm going to say 4 kilograms. I'm liking 4 today, I guess. We got a mass over here. This could maybe this is a person over here. Maybe this is a table. I don't know why we're balancing it in the system, but we are. This could be some arbitrary system set up for you. And believe me, when you look through the textbook, you're going to find some very arbitrary systems. We're going to call this mass 1 over here, and I'll say it's 20 kilograms in mass. Now there's this unique little spot here. This is called a fulcrum. There's just a point that's helping to balance the board. If this were a seesaw without the wire, without this cable over here, it would likely, definitely, depending on the mass over here, of course, but it would likely rotate clockwise and hit the ground, if that's the case. So I'm going to give a mass 2 over here of 40 kilograms. And indicate to you all that this cable here is holding the end and keeping it from rotating downward. Okay. So my big question is, with this system, there's 2 pieces of information we can actually find from this. What is the tension in the cable? See, this is going to tend to rotate clockwise. So this cable is going to be tight, and it's going to keep it from rotating clockwise. We can find that. Something else we can find is the normal force applied to the board from this fulcrum. So these are 2 bits of unknown information we're going to work with here. And there's one last thing I want to talk about, and it's getting back to this board that's holding everything up. I'm going to assume this is a uniformly dense board, meaning its mass is distributed evenly throughout this thing. So something that's going to be important to take note of is that when we apply a torque from the weight of this board, we're going to apply it at the board's center of mass. So think about the center of mass somewhere about right there. This is the center of mass of the board, and that's where its 4 kilograms of weight is going to be applied to the system. All right, so I think we're all ready to set up. I'm going to draw a new force diagram, and this force diagram is going to include an approximate shape of the board. We're going to place forces along the board where they're being applied to it. So there's a tension over here that's unknown. There's a normal force right here that's unknown. The weight of the board is focused at the center right here. So I'm going to say the weight of the board. And we've got a mass over here causing a weight at this end. So I'm going to say FG1, talking about mass number 1. And then we got a weight over here. We'll call it FG2, the weight of mass number 2. All right, and that's our system. And when it rotates, this is going to be the point of rotation. Okay, this is the rotation axis. So it's often very useful and important to take note of where the rotation axis is. That point is where it's being held. It's not allowed to translate through that point. There are no side-to-side forces, so this board won't slip off. It'll just tend to rotate, at least at first. Of course, when it hits the ground and bumps, it might actually rotate a little bit off that fulcrum. But this initial rotation will be about that point because it's not free to translate up or down. Okay, so that's a rotation axis, and whenever you put that in, that just means that point is not going to be rotating. Any forces along that are going to apply 0 torque because there's a 0 torque arm. Whenever a rotation axis is given, that's your reference point. Okay, that's where you want to measure your torque arms from and all that kind of stuff. In some of these scenarios that you're going to see, there's not an apparent point where there's going to be a rotation axis. You won't really know where that center of mass of the system is, or it tend to naturally rotate. So if that's the case, you can pick any point you want, any arbitrary point. But in this one, we do have a rotation axis. So what can I do? I can go right to Newton's second law for rotation. Sum of all the torques equals I alpha. And again, what we want to do here is set alpha equal to 0 for equilibrium. We're trying to find an equilibrium state and determine the tension force and this normal force over here. All right, if this is our point of rotation, then which of these forces will cause a clockwise rotation and which will cause a counterclockwise? You look over here, everything going in this direction, causing a rotation like that, would be a counterclockwise. But also consider, what about any forces over here? Would any forces cause like an upward motion on this side? And what forces over here would cause a downward motion? Those would be clockwise forces. Anything that goes counter to that would be counterclockwise. So right now, as I'm looking at this, the normal force would give 0 torque. It's being applied at that rotation axis. So the torque arm there is 0. Don't need to worry about that one. The weight of the board is going to be causing a clockwise rotation. It's going to be pulling down at this point, trying to pivot around that rotation axis. Weight number 2 is also going to cause a clockwise rotation, where this tension is going to try to balance that with a counterclockwise rotation, along with being helped by weight number 1. Do you see how this is going to cause a clockwise rotation? In that kind of view. Okay, I'm going to clean this up a little bit, but I was just trying to illustrate there what should be positive, what should be negative. You can also pick a positive direction for your R value, and any negative R's you could plug right into the R cross F as a negative R cross F, and that would also give you the correct sign. All right, so I'm going to call counterclockwise as my positive direction, just to state a direction there. We've got weight number 1 being applied at 1 meter of distance. So there's torque 1. I don't know why I put a plus sign there. There we go. And now move over to the next force. Normal force has 0 torque arm. I could put it in here. Normal force times 0 torque arm. Of course, we don't know what angled direction that is because there's 0 torque. Is it going to be clockwise or counterclockwise? Neither. There's 0 torque there. FGB, this is going to go clockwise. So since counterclockwise is positive, I'm going to subtract the weight of the board times its torque arm. Let's figure that out. From the rotation axis, the center mass is exactly 1.5. And we know that's going to be 1.5 because it's a 5 meter long board. And the center mass is at the very center, at 2.5 meters from the end. So 2.5 meters is only 1.5 meters away from that fulcrum, from that rotation axis. There we go, weight of the board. Now I got this FG2, and that's also going clockwise. Clockwise is my negative direction. So weight number 2, and where is it? Its center mass is right over this point, which is 1, 2, 3 meters away. And finally, we've got this tension. This tension is pulling up in our counterclockwise direction. So that's going to be a positive tension. It's trying to keep this system balanced. And the weight over here is working with it to balance out these two other forces. All that equals I alpha. Oh no, what's I? Do I have to figure out this, I, the moment of inertia of each of these masses of this board? No, because remember, if alpha is 0, then I is going to just be, not worthy of putting on there. It's not worth putting on there. Maybe it's worthy, but not worth it. All right, so there we go. And before we move on, let's just check this out and make sure I've got everything here. I've got each force times a torque arm. And oh, look at that right in there. What am I missing? I'm missing a torque arm for my tension. That is, let's see, 1, 2, 3, 4 meters away. That's where it's positioned. So this isn't just T, it's T times 4. It's easy to forget. I did it that time. So check out each step. Really recommend it. Now this next step, we're going to be inserting some weights. So I'm just going to simplify it a little bit. We're going to use a G of 10 meters per second squared instead of 9.8, just to make this math a little bit easier. Over here, FG1 is 20 kilograms, so we're going to have 20 times 10. And I'll just put that 1 in there so we remember the torque arm. Of course, the normal force's contribution to torque is 0. And we've got the weight of the board, 4 times 10 times its torque arm of 1.5. FG2 is the 40 kilogram mass, 40 times 10 times torque arm of 3, and we've got 4 times the tension. Torque arm times the tension equals 0. Okay, solve this as quickly as we can here. 200 minus 4 times 10 is 40, times 1.5 is 60. And then we get a 400 times 3 is 1,200 plus 4t equals 0. All right, combining these, we get a 1260 minus 200 is a negative 1060. And if I bring the 4t over the other side, we get a negative 4t over there. Dividing both sides by negative 4 is going to give us our result for the tension. All right, 4 goes into 1,250 times, and another 15. So 265 is the Newton force for the tension. There it is. All right, does that make sense to us? Are we done? Let's check it out. 265 makes sense. We've got 400 newtons going down. Got another 40 plus, oh, there's a little bit of help over here. So like 400 newtons over here, plus another, there's some torque pulling it this way. There's a 200 going this way. So around 200 something is probably just about right. But wait a second, we're not done yet. We also need to find the normal force. Okay, can't forget about that. That's part of our target. So, oh gosh, how do we do that? We've got a sum of the torques expression, and look what happened to the normal force. It got zeroed out. We actually can't use this torque equation to figure out the amount of normal force. You might be saying, well, is it supporting any weight? Well, yeah. Without that torque there, without that fulcrum, it's going to rotate downward about this point. It's going to just kind of hang there from the string and rotate down that way. So it's got to be pushing up on the system, but we can't use rotation for that because it has a 0 torque arm. So when you get stuck, don't stop. Remember, we also have Newton's second law for translation. You see this system, what is IA? F equals MA, surely. There we go. You even got a shirt that says that. May the MA be with you. There we go. We can't forget this. The system is not only in rotational equilibrium, it's also in translational equilibrium. All the up forces should equal all the down forces, and that keeps it from translating up into the air or down into the ground. So both of these are true when the system is in equilibrium. Now I am running out of space up here, so I'm going to bring it down. We're going to party on the bottom, try to find that normal force by using Newton's second law for translation. Now in this scenario, we're going to have the tension up, we're going to have the normal force up, and we're going to have the weight of the board going down, we're going to have the weight of that mass 1 going down, and the weight of mass 2 going down. And that's all we got to look at this like. We've got 2 forces up and 3 forces down. So let's sum them. We're only looking at the y direction here. Got the tension going up. We got the normal force going up. We've got F1 going down. That's our 20 kilogram mass. Let's look back at that. So it's a 20 kilogram mass pulling down. We got the weight of the board pulling down and the weight of the 40 kilogram mass going down. The weight of the board is from a 4 kilogram mass. I need some more space here. Let's do this. Okay, so weight of the 20 kilogram mass is 20 times 10, and that's going down. We've got the weight of the board. That's a 4 kilogram mass, 4 times 10. And the weight of that 40 kilogram mass, 40 times 10. And all that equals MA. Now I can sum up the mass of all these things, but you know what? The acceleration is 0. We're still in equilibrium. Remember that. Acceleration is still 0 for equilibrium. Okay, what about this? We got 2 unknowns. No, we don't. We know the tension is 265 now. 265 plus the normal force minus 200 minus 40 minus 400 equals 0. Okay, we have a negative 640 plus 265. So our normal force, we bring that 640 over to the other side, 640. Subtract the 265 from it. We end up with 375 newtons. Okay, let's see if this makes sense. See if I did my mental math correct. We have a total of 500, let's see, 65 plus 75 is 140, so 640 newtons going up. And look at this, 640 newtons going down. That balances out our system. We've got a normal force and a tension. We solve for our unknowns. Everything makes sense and checks out. All right, I've got 2 more scenarios here. If you want to keep going, keep going. This is a long video, but whenever you feel like you might need another look and some more perspective, come back and watch the rest of these. But this is probably enough to get you going if you want to start out your book work or whatever you're working on now. All right, here's a similar system. This time I've got a pivot. It's kind of like a fulcrum, except you can't lift this off the pivot. It's pivoted on this point. You can push to the left or to the right or up or down, and that point isn't moving, so it's fixed there in space. Over here, I've got a cable attached to a wall and a board. Now I have less stuff going on here, so hopefully that'll make it a little bit better. This board, I'm going to give it some weight again. I'm going to call this a 4 meter long board, and I'm going to give it a little bit more mass, 10 kilograms. Okay, the board. Again, it's uniformly dense, so the mass is uniformly distributed in this board. I'm going to mark a center mass. Sometimes that's really good to put on your paper, just so you don't forget about that as an object that's involved here. Let's use 20 kilograms again as this mass. And what I'm looking for here is the tension. Okay. Now, in this scenario, there's going to be something a little bit unique here. This pivot is actually part of our system in here. It's keeping everything in equilibrium, or helping to. This tension over here is keeping the board from flapping downward. But this pivot's also keeping everything from translating. So there might be a force here. There is going to be a force here acting on this pivot. So I'm also going to look for the force on the pivot. Let's consider what these 2 pieces are going to be. And this one's a little funky to think about, and that's why I want to talk about it in this video. So if you see a situation like this, you'll be able to solve it. Okay, what's the first step? Draw a force diagram. And we got a tension here. Oh, one thing I guess I'm missing here is we would need an angle. This would be part of the system. So if the board is held horizontal, when this angle is, we'll call it 15 degrees. Okay, that looks kind of like 15 degrees to me. I'll draw that a little bit, write that a little bit better, more clearly. There's that little angle there, okay? So we're going to have a 15-degree angle for tension T. There's the weight of the board, force of gravity, or the weight of the board, acting at the center there. There's a weight of this 20 kilogram mass. I'll call it FG. There's only one mass here, but it's a little easier way to handle that. And then finally, there's this pivot spot over here. Okay. Now, with this weight pulling down and an FG over here, you might imagine that at this pivot, there's an upward force to it. Okay, I'm going to call this FP in the Y direction, a vertical upward force to the pivot. Think of it this way: if you had a hand holding on to the end of the board there, you'd have to lift up to keep that side of the board from falling down. So there's definitely an upward force there to keep it from falling down. I got a little ahead of myself there too. Look at this tension; it's pulling up, so it's supporting some of that weight also, but it's also pulling over to the right. So up and right. What's that mean about the pivot? If this system is in translational equilibrium, then this pivot is also going to have to pull to the left. I'll call it force of the pivot in the X direction. And this is what you often see from pivots. they hold some of the weight, but they're also balancing out any of the horizontal forces that are in the system. For example, if this tension were actually pulling toward the inside, then this pivot would have an inside kind of a force to counteract that. It's sort of like a normal force here. It's working against the pressure on it. I hope that makes sense to you. So there's an X and a Y component to the pivot that we're going to put together in the end to find out what that force is going to be. Okay, so this evidently involves some rotation. I'm going to use this as our axis point, a little axis here. I like to keep a view of that with all this monochromatic mayhem. And let's get ready to sum all the torques. We want everything to be in equilibrium, so we're going to use an alpha equals 0 for equilibrium. And let's check out these torques. From this point, we've got the weight of the first mass, and it's a distance. This is a 4 meter long board, so I've indicated this as an increment. This would be 1 meter, 2 meters, 3 meters, 4 meters out here. Okay, so this weight is at 20 kilogram mass is at 1 meter from that pivot point. Then we've got the weight of the board. So I've got the weight of the board, and it is 2 meters away. The center of mass is located exactly at the half mark. This is a uniformly dense board. All right, so this weight is pulling down. That weight is pulling down. What about the pivot? Does that apply any torque? I kind of skipped past it because my brain said it's okay. It doesn't apply any torque because there's a 0 torque arm. Whatever that force is, it's times 0 for the torque expression. So we don't really need to worry about that pivot. And finally out here, evidently I've been causing a clockwise rotation to be positive. This tension, though, is going to apply a counterclockwise torque. And I'm going to try to let this cross product take care of itself. The torque arm extends from the rotation axis out to that point where the force is applied. Okay, so if we have a torque upward, we're going to have to go, let's try to get it from your perspective using the right hand rule. R goes out this way in the direction of the R, the torque arm. We have to rotate our hand upward to slap that tension. So R cross T would give a right hand roll rotation this way. And if you look at that, that's a, what kind of rotation is that? That's a counterclockwise rotation. So we're going to have to indicate a negative sign here for a counterclockwise rotation. And the tension T times the torque arm is 4. But we can't forget that there's going to be a little sine 15 in here. In other words, if you really look at it, isn't it the sine component of this little triangle that I form here? Isn't the sine component that applies a perpendicular force to that point? That's what it is, and that's where that sine 15 comes in. So if you either want to look at it as an R cross F, or think of it like the perpendicular component of the tension times F. You could do it that way also. Both of those will help you arrive at the same torque value. So just double check these. We've got a force times torque arm, force times torque arm, force times torque arm, and I've included that angle in there. The pivot force has no torque. So I am done summing the forces. I'll go back to my white monochromatic awesomeness. That's what I did there. And we're going to have a 0 on this side again. I love equilibrium. Let's move it on. The weight is 20. We're going to use a G of 10 again. Always indicate that if you're going to use 10. And weight of the board is from a 10 kilogram mass. So 10 times 10. And its torque arm is 2. Now over here we've got a 4 sine 15. I'm getting away from the easy to work with numbers here. 4 sine 15 is 1.035. I'll say 1.04. 1.04 T. I often like to, whenever I'm making up some numbers here, I like to keep 3 significant figures. That gets us always within 1% of any other answer you might come up with. All right, so 20 times 10 is 200. 10 times 10 times 2 is another 200. And if we add 1.04t to the other side, we're going to get a 400 divided by 1.04. So our tension is 400 over 104, 1.04, 384.6. I'll say 385. There it is. Does this make sense? Yeah, we got like 200 grams there, or 200 newtons there. We've got another 100 newtons there, total of 300 newtons. So 300 newtons of weight with 385 newtons of tension force. That makes sense. This tension is pulling out not only up but also to the right. We also got this pivot over here as well. So what's it going to be doing? Okay, so I'm gonna trust in that, and we'll come back and see if that makes sense in the end. Now we got this pivot again. We got a point here that had no torque. So let's apply Newton's second law. If we try the y direction, what's that give us? Well, the y direction will help us to look at this y component over here. And the x direction, we'll compare this force of the pivot in the x direction to the horizontal component of tension. So we're actually I'm thinking we're going to need both directions of Newton's second law. We don't just have a y direction like in the last one, but there's a horizontal type of action going on here. All right, in our y direction, we're going to have the pivot's y component going up. We've got 20 times 10, the weight of that 20 kilogram object going down. We've got the weight of the board, 10 times 10, going down. And going up is t sine 15, that vertical component of tension. All that equals 0 acceleration times mass. Okay, so the pivot's y direction force is 200 plus 100 is 300. So I'm going to add that to the other side, 300. And then we got this t sine 15, which we're going to subtract on both sides. So I'm going to subtract 385 sine 15. And that should give us a y component force, 300 minus 385 sine 15. 200.35. So that's just about 200 newtons. Okay, we got 200 newtons there for that y component. All right, let's see what else we have. Okay, we've got the x direction now. Let's move it on. We sum the forces. What is that? I think it's a new Greek letter. It's called BAMA. Oh, sorry, new Greek letter. Sigma for the pivot in the x direction equals ma in the x direction. So here we go. In the x direction, we've got, oh, this is a little easier. If I'm calling left positive, I'll say the pivot's x component. I thought something looked a little funny there. This is sum of all the forces in the x direction. It is the end of the day, and Shelley is still making videos. It's for the children. Okay, moving on. Now we have the x component. The y component of the pivot force doesn't have an x component. These weights don't have x components. Only this cosine 15 components, the cosine component of the tension over here, has an x component. So if left is positive, then that makes this negative t cosine 15. And we've got translational equilibrium, so the acceleration is 0. All right, moving on down, we're ready to do this. Fpx minus tension is 385, cosine of 15. So the x component of The pivot is 385 cos 15. 372 newtons. A lot of force on that. Okay, a lot of force on that. It's supporting a lot of that weight, it looks like. Okay, so what's the overall pivot force? It is going up and left because we got positive values for those. Up and left. By how much? The upward component is 200 right here, and the x component is 372 going this way. So the overall force is that one, or FP. FP is the Pythagorean theorem applied to that. So square root of 200 squared plus 372 squared. It's 422 newtons. There it is. So does it make sense that the pivot force is greater than the tension? Well, let's see. Yeah, I think it does. More of the weight is distributed on this side of the beam. So the pivot is pulling away from that tension and up. We could also find a direction. All right, the angle here. What angle is that going to be? It's going to be 372, the inverse tangent of 372 over 200. A lot of stuff we can figure out from this. See how it compares to 15. And it's 61.7 degrees. That's actually, this angle here is a bit steeper. F pivot is going this way, about 62 degrees there. Okay, so now we have a solution for that one. Finally, got one more scenario here, if you need more. And this final scenario is a ladder. It's leaning up against a building. With the infamous ladder problems, there's always some kind of friction involved. You see this ladder has a tendency, if there were no friction, what would it do? It would kind of slide outward. Like a moment later, it'd be like this. A moment later, after that, it'd be like that. And it would just, the top would fall down, and the bottom would slide out. That's the motion it would tend to have if there were no friction. So a question that might get asked is, let's say for a person near the top who's climbed that ladder and is positioned about, right at this point. We'll say about 3/4 of the way up. What friction? What coefficient of friction is needed down here? The static coefficient to keep our system from moving. Now let me give a few bits here that would be helpful. First off, there is a bit of friction up here. It's sort of, in a way, kind of like a pivot point. There's a contact between the ladder and the wall. The wall pushes outward with a normal force, and it is trying to keep this ladder from sliding downward with some friction. So it seems a little, not very intuitive if you haven't thought about this scenario before, but there's some friction upward and some normal force out. And that's the two contact forces involved. Down here, the tendency of the ladder at the bottom is to slide out this way if there were no friction. So there's some friction holding in this direction, and also some normal force. Now, are those two normal forces equal? No, they're not going to be. So this is from the floor, this is from the wall up here, and those are the two forces. Those two contact forces are what's holding on to them. Collectively, a couple of normal forces and a couple of frictions. Also involved, we have the weight of the person on the ladder and the weight of the ladder itself. So there's a couple of weights we're going to draw out here. I'll say weight of the person and weight of L, the ladder. Let me give a few pieces of information here. Let's say that the friction between the wall and the ladder is negligible. Let's say this friction is 0. So we're not going to rely on friction from the wall at all to keep this system from moving. That means it's only the friction, the mu from between the ladder and the bottom, that's going to be important here. And that's generally what ladder manufacturers will focus on. They're not going to be counting on friction on the wall to keep this thing from sliding. Oftentimes they'll put these feet at the bottom that either dig in really well, if this is an aluminum ladder that goes really high. Make these adjustable feet that either have rubber pads or they can be rotated so they have these claws that dig into like a soft soil, ground type of thing. So we're going to say 0 friction at the top. Let's give a mass of 80 kilograms to this person. Mass of the person is 80 kilograms. And I'll assume a 10 kilogram ladder. There it is, rather heavy ladder. Okay. Draw ourselves a force diagram. There's one piece we're missing here though. Let's go a 60-degree angle for that ladder. So what is the minimum mu, static coefficient of friction, to allow a ladder to be placed at an angle of 60 degrees and not slide? Okay, I'm going to redraw these forces just to try to clean things up a little bit. Got the weight of the ladder, got the weight of the person. Normal force up here, I'm going to say normal force from the wall. And of course there's going to be a normal force from the ground, that perpendicular contact force. And like I said before, the ladder will have a tendency to slide outward. I didn't have a vector there. Have a tendency to slide outward, so there's going to be an inward frictional force. To make these a little bit more bold, there's that monochromatic mayhem again. Let's get some two tones here. There we go. So we can more easily see these forces. Okay. According to this, something we can look at is, of course, Newton's second law for translation. And if we just stick to translation, I wonder if we'll be able to figure out what's going on here. So let's try it out. If we just tried translation, would we be able to determine this? Let's give it a go. If we sum the forces in the x direction, what have we got? On the x direction, we got the normal force from the wall going to the right, and this friction going to the left. And that's it. Those are our right and our left forces. That's all we have here. And that equals mass times acceleration. But we want our person on our ladder not to be accelerating. So all that's equal to 0. Of course, we don't know anything about the normal force from the wall. But substitute, what is friction equal to? It's mu s times normal force. And that normal force would be due to the ground. So this would be the contact force for this friction force is from the normal force of the ground. That equals 0. Okay. So far we can't solve it yet. We've got the normal force from the wall minus mu s times normal force from the ground. We have no idea what all three of those are. We got 3 unknowns there. And that might be a little clue to you that we're going to need 3 equations. So let's see. What about the y direction? This will be a second equation. In the y direction, we have, translationally, we got the weight of that person going down. We've got the weight of, I'm going to do this a little backwards. Let's make down negative, up positive. So weight is negative. We've got the weight of the ladder going down. and we got the normal force from the ground going up. Okay, and that equals mass times 0 acceleration also. I think we can figure some things out here. The weight of the person is going to be, we're going to use g of 10. Just define that. It's okay to do that as long as you define it. It's very acceptable in these kind of problems. So mass of the person is 80 kilograms times a g of 10. And we got the weight of the ladder also. So that's going to be 10 times 9.8 or times 10 plus the normal force on the ground. And just like in any other translational equilibrium problem, all the down forces equaled up all the up forces, and if there's only one normal force, the normal force going up is generally balancing all the weight. So here we have the normal force on that ground would be equal to, we got 800, negative 800 minus 100 is 900 newtons. All right, so we do have that one piece here. Plugging it in up here, normal force of the wall minus mu s times 900 equals 0. But you see, we still have two unknowns. We don't know the normal force on that wall. So what do we do when we're stuck? Don't stop. Remember, the system might rotate. If it slid out, it would tend to rotate downward. So what I'm going to do is pick a point where we're going to have the normal force on the wall as one of the things that it's going to be in this rotation. Since there's not an obvious rotation point, I'm going to pick one that should help us out. And if I pick a rotation point here, a reference point for torque, for summing torques, what's going to happen here is that one of our unknowns that we need to keep involved is going to be canceled out. Its torque arm from this point is 0. So in preparation for summing the torques and setting them equal to 0, because alpha is going to be 0, this is a static scenario. Equilibrium is happening here in rotational and translational forms. We need to pick a point where this is going to be involved. And what I mean is, you can pick up a reference point anywhere along here. It could be the center of the ladder. It could be right here in this arbitrary spot. But you know what? I'm going to pick right down here. And the wonderful thing about that is the torque arm for this normal force on the ground and the friction is 0. So that those won't be involved in this equation. Just kind of makes it work out a little bit more easily mathematically. The only other things that are going to be involved is the normal force on the wall, the thing we need to know, and known weights causing torque. In other words, pick a nice convenient spot to be your rotation point. Remember, in outer space, if this ladder was floating along, it could rotate about any point. It's most likely to rotate about its center of mass. If you stick it to the ground, it could just as well rotate this way to lift up off the wall. So pick any arbitrary point, and we'll look at torques. Sum of all the torques. It's equilibrium anyway, so it doesn't matter. Long story short. The normal force on the wall applies a right hand, or let's say a clockwise torque. So let's start with that. We're going to have the torque from this wall. Normal force from the wall. The torque arm is, I don't think I gave that information. The length of our ladder is going to be 4 meters. That's 1 meter here. That's another meter to the center of mass. And here we are at the end. So the torque arm to that between our reference point, call it ref, and the normal force from the wall is 4 meters. This is not a perpendicular force though. The torque arm is in this direction. So what we need to find is the angle between the torque arm and the normal force from the wall. And that's the theta we're going to plug in here. If we drop a line straight down at that point, we can see that it's going to be 90 degrees plus a little bit in here. Now this little angle corresponds to, if I dropped a 90-degree angle here, or a perpendicular line there, normal, and we looked at this piece right there, that's going to correspond to this little piece here. We've got a couple of bisecting lines, or a couple of parallel lines with a bisector through it. So therefore, this little angle here is going to equal this little angle down there. And since we have a normal force that's perpendicular to that, it's going to be that 90 degrees plus that little bit of angle. Little explainer for a long story short, it's going to be 90 plus 30 degrees. This is 60 degrees here, so that makes this angle 30. And 90 plus 30 gives us 120 degrees. All right, so that's the torque on this point due to the normal force from the wall. Now we've got two counterclockwise torques. One is from the weight of the person, and that person is 3 meters away from our reference point. And the angle between R at that point and that force, this one's going to be 90 degrees plus 60. Or another way to look at that is the torque arm is almost 180 degrees away, but it's actually 180 minus that little 30 degrees. In other words, look closely, think this one over, that angle is going to be 150 degrees. And the same thing for the ladder here. The angle between R and the weight is 150 degrees. So we'll have a F, G the ladder. The center mass of the ladder is at 2 meters. Now I'm running out of room here. We'll have a sine 150 on that one also. I just moved that over a little bit. So we have a sine 150. And all that equals 0. Get rid of my old sine 150 there. So everything there equals 0. Try to work on with some more room here. All right, sine 120, sine 150. We're going to need to know those. Sine 150, I have a guess is going to be 1/2. So sine 120 though is 0.866. Party pooper causing some problems to my my numbers here. Gosh, those uneven numbers. Then we got the weight of the person. That's 80 times 10. Torque arm is 3. And sine of 150 is 1/2. You got the weight of the ladder. 10 times 10 times 2 is a torque arm. And sine of 150 is 1/2. All that equals 0. All right, 4 times 0.866, sorry. 4 times 0.866 is 3.464. Go ahead and keep all those just because I feel like it. All right, 800 times 3 is 2,400 times 1/2 is 1,200. And we get 200 times 1/2 is 100. And look at that. Normal force in the wall is equal to, we're going to have 1,300 divided by 3.464. $375 newtons. What good is that? Well, now we're ready to find our final answer here. If this is a 375 Newton normal force in the wall minus mu s times 900 equaling 0, then our mu s is a wonderful, we're going to have a 375 divided by 900. That's our minimum mu s to keep this ladder up at 60 degrees. 0.416. I'm going to say a 0.42. There it is. You can always arrive at the answer no matter how crazy the math gets. We started with 3 unknowns. And that means we need 3 equations to solve it, given some very measurable values like weights of objects and orientations. The rest of it, the stuff like normal force on the wall and such, we worked it out with summing forces in the x direction, the y direction, and summing torques. Newton's second law works for everything. If you get stuck, don't stop. Remember, you've got one more equation to pull out all the time, and that'll get you there. This is the end of this very long episode. I hope some of these will be useful throughout. If you held on through this entire episode, way to go. But just remember, if you've come back to this, I hope these 4 examples are going to help get you through the next few days and give you lots of examples of how to avoid errors like I almost made, and how to look at these kind of brand new situations involving systems that can possibly rotate. And that's it. This is the end.